In this video, we're going to talk about the present value of simple ordinary annuities. Suppose Sophia wants to deposit money now at 6% per annum to guarantee that she'll receive payments of $100 per year for the next 4 years. We'd like to know how much she should deposit today. The purpose of this question is mostly for us to come up with a formula. We're going to develop a formula here. So what we're going to do is we're going to put this scenario on a timeline. Since Sophia's opening the annuity today, she doesn't owe a payment until the end of the first period, which in this case is 1 year later because the compounding is annually and it's a simple ordinary annuity. So what we're going to do is we're going to say the present value today of the $100 a year from now is 94.34. She needs to put 94.34 into the bank today with the current compounding interest situation to ensure that she'll have $100 a year from now. Well, she needs to put $89 in the bank today to assure that she'll have $100 2 years from now. Okay, figuring out the present value of the $100 3 years from now, we see that it's 83.96. And the present value of the $100 4 years from now is $79.21. So she needs to make sure that she has all these sums of money today so that in the future she can withdraw these sums of money. So our job is going to be to add up those 4 sums of money, and we see it's $346.51. So the present value is $346.51. So that's how much she should deposit today. Now, we would like to come up with a formula so that in more complicated situations, we don't have to do so much math. So what we recognize right away is that what we have here is a geometric series where the first term is 100 times 1.06 to the negative 1, and that each subsequent term is simply equal to the prior term times 1.06 to the negative 1. So we can use the sum of a geometric series formula, letting A be 100 times 1.06 to the negative 1, letting R be 1.06 to the negative 1, evaluating it, and we get the same amount. So we see that we can do that. So what we're going to do is see if we can simplify this a little bit. We have Sn equals A times R to the n minus 1. We've established that A will be equal to R times 1 plus I to the negative 1. In our previous example, it was 100 times 1.06 to the negative 1. We see that our R value will be 1 plus I to the negative 1. In our previous example, it was 1.06 to the negative 1. We leave n where it is, and we have another r on the bottom. Okay, so now what we're going to do is we're going to multiply this negative 1 and this n. We're going to have negative n here. We can then, if we want, distribute into the bracket of the numerator 1 plus I to the negative 1. Okay, and doing that leads to negative 1 adding to negative n gives us negative n minus 1. And then this 1 plus I to the negative 1 multiplied by negative 1 gives us minus 1 plus I to the negative 1 in that as well. And we have R not distributed into the numerator. R stays on the outside. The denominator is as you see here. We're going to factor 1 plus I to the negative 1 from that numerator. So we see that if we take this 1 plus I to the exponent negative n minus 1 and divide it by 1 plus I to the negative 1, we will end up with 1 plus I quantity to the negative n, and that's what we have here. When we take 1 plus I to the negative 1 and divide it by 1 plus I to the negative 1, we have 1. So our numerator is as you see here, and our denominator is still 1 plus I to the negative 1 minus 1. Now we're going to multiply top and bottom by 1 plus I. When you take 1, I want you to look at this factor of the numerator. When you take R times 1 plus I to the negative 1 and multiply it by 1 plus I, all you're left with is R. That's what we have on the outside. Downstairs, we have 1 plus I, and we're going to multiply it by 1 plus I to the negative 1 minus 1. Well, 1 plus I times 1 plus I to the negative 1 becomes 1 plus I to the 0, which is also known as just 1. And 1 plus I times negative 1 will end up being minus the quantity of 1 plus I. So we'll see that on the next screen. And that's what we get here. Our numerator had been established a moment ago. Our denominator is 1 minus the quantity 1 plus I. Distributing that minus sign in, we get 1 minus I, which ends up being negative I. And we can leave the formula like this if we want, but a lot of times you'll see people multiply numerator and denominator both by negative 1. Multiplying numerator and denominator both by negative 1 has the effect of switching the order of these two terms and leaving a minus sign in the middle, as well as making that denominator positive. And what we end up with is a formula. Now, since the sum of the geometric series in this case is the present value, or what needs to be deposited today, we can change that to PV. And we have R as the regular payment, and we're multiplying by this quantity right here. So what you see in a box is a formula that a lot of students enjoy using. And we'll now see if we can answer a couple of word problems using that formula. Now, before we go any further, let's make a distinction between the future value of an annuity and the present value of an annuity. We use the future value of an annuity formula when we have a scenario where all the regular payments lead up to a large sum of money. Examples include saving for retirement or college or some other event in the future. We use the present value of an annuity formula when there's a large sum of money now and then regular payments are going to occur after that. Examples of that involve receiving a bank loan or a mortgage on a house, or depositing money now to assure that you're receiving payments later, or financing a present purchase by making future payments. So one of the things that students have to be able to do is determine in a question, are they asking a future value question or a present value question? So suppose Clarabelle wants to deposit a specific amount in a simple ordinary annuity at 4.5% per annum, so that when her nephew goes to college, he can withdraw $500 per month for 4 years. We want to know how much Clarabelle should deposit today and how much interest will be earned in the 4 years. So the regular payments are going to be $500 because Clarabelle is trying to ensure that her nephew can make regular withdrawals of $500. The I value is 0.045 divided by 12 because it's 4.5% per annum, and she wants him to be able to make regular monthly withdrawals, so we're divided by 12. So N is 4 times 12 because he wants to be able to do this for 4 years, 12 times a year. So the present value of the annuity will simply equal this formula here if we plug in these numbers. So plugging in those numbers to that formula leads to $21,926.40. So what we're saying is Clarabelle should deposit $21,926.47 today to assure that her nephew can make these 48 future withdrawals of $500. Okay, so let's think about the interest earned. So the total payments are $500 per payment times 48 payments, which is $24,000. So in the future, this nephew will receive physically $24,000, but Clarabelle only has to deposit $21,926.47 today, meaning there's a difference of $2,073.53. That's the interest earned, and that is compound interest working in Clarabelle and her nephew's favor. Imagine Yasmin purchases a car for $9,999. She makes a $2,000 down payment and finances the rest. She's going to make monthly payments over 3 years at 12.9% per annum compounded monthly. We want to know what her monthly payments will be and what the total interest will be that she pays. So after making her $2,000 down payment, Yasmin's total amount owing will be $7,999. So that's the present value. She owes that much money. Okay. We don't know what her regular payment after that will be. We know the I value will be 0.01075 because it's monthly payments, so we're dividing by 12. We're doing this for 3 years, so N will be 3 times 12, which is 36. And so we can say that our 7,999 present value will equal R times this number here. Doing some fairly simple math to isolate the R, we see that R will be $269.13. So what we're saying is for this $9,999 car, Yasmin's going to put down $2,000 as a single time down payment, and then she's going to pay $269.13 12 times a year for 3 years. Okay? So her total payments will be $269.13 times 36, which is $9,688.68. That $9,688.69, we're going to subtract $7,999 because all she really owes is $7,999. But instead, she's making a promise to pay in the future $9,688. So she's actually making $1,689.68 additional. She's giving extra money in that amount. The interest that she's paying is $1,689.68. Okay, so it's important to keep in mind that when you purchase a car, if you've got a really high interest rate like that, you're going to be making this number quite a bit higher. So if you can get this, if you don't have the money for a car, if you can get that number to be low, then this number will be low and you won't have to pay so much in interest.